Let's talk about applications of the derivative, but let's start in first calculus. Let y equal s of t give the position of an object moving on a number line. So I have a number line and an object on it. I can think of that as the s-axis. Every time I plug in a value t, I get out a position, right? So maybe my object moves this way for a while and then goes back that way, and I'll let that be the positive direction and this be the negative direction. And in terms of direction of motion on a number line, that's all I need, right? I'm either moving right or left. I'm either moving positively or negatively. Okay, so the position is s of t, and we know that when I take a derivative, I get velocity. Velocity, in this course, we've thought about it as a vector. Well, in this one-dimensional case, just a plus or a minus is enough to indicate the direction of motion. Acceleration, well, that's the next derivative down. So the first derivative of velocity, or the second derivative of position. Speed is the absolute value of velocity. It's how fast you're going without that information about direction. So we don't need to know whether we're moving to the right or to the left. Okay, but now let's say instead of moving along a straight line, we're moving along a curve in space. So r of t is a vector valued function that gives me the position of an object moving in space. The position is r of t. You plug in a value of t and that vector points to where you are in space. The first derivative, dr dt, that is velocity. The velocity vector is dr dt. And in our last video, we had a little sketch where we saw that the vector formed by taking the derivative is tangent to our curve, and that makes me think it's velocity. But also, if I just look at this, this is the position on the x-axis, that's position on the, position of the x-coordinate, position function for the y-coordinate, and a position function for the z-coordinate. And if I take derivatives of each of those, I get this derivative, right? Well, the derivative of position in each component is velocity. And so the first derivative of position is still velocity. I take the derivative of velocity and I get an acceleration vector. So I have these same rules, just with vector functions. Speed. Speed is how fast I'm going without information about direction. So instead of an absolute value, now I have to think about magnitude. The magnitude of the velocity vector is the speed in which we're traveling, right? How long that vector is indicates how fast you're moving. So it kind of matches what we did in first calculus, and it matches the notion of size of a vector, right? The length being the magnitude. Speed is the magnitude of velocity. The direction of motion now isn't just a plus or a minus. It's a unit vector. The direction of motion is the unit vector that is velocity over its own magnitude. Right, because if I think about a curve in space, the velocity vector was pointing tangent to my curve, so if it's pointing that way, it means in that moment, my point is moving that way. This vector gets a name. Your author waits a few sections before revealing it, but this direction of motion vector is called big T, and it's called the unit tangent vector. Which is a great name for it because it's 1 unit long and it just touches that curve in one point near the point, right? It's literally tangent to the curve. All right, so those physical applications are really important. They're the same ones we're used to from Calc 1. One other concept is the idea of tangent line. The tangent line to r of t at t equals t naught is the line passing through r of t naught, literally giving me a point on the line, right? That's the point on the curve. and in the direction of the velocity vector. Right? If I think about my curve, my velocity vector is pointing in that direction tangent to the curve. So to find the tangent line, I want a line that's parallel to that vector that touches the terminal point of r of t naught. And so we could even find tangent lines just by evaluating the position function to find a point on the graph, and then knowing that my velocity vector is parallel to that line.